Got everything you need?
Mm-hmm.
Okay.
I think so.
Good.
Laser pointer's working, yeah.
That's good.
Got my microphone, which is going to be unmuted.
Okay, it is 4 o'clock. So I have the great pleasure of introducing Tracy Slotnier, who many of you will remember was a very fine student here working with Doug. And the reason I'm up here instead of Doug is that Doug is off on sabbatical, and so I'm happy to do this. But let me give you a few details of what Tracy's been doing since she was here. She, of course, got her degree here in 2010 with Doug, and has been doing great things ever since, and of course was doing so before in Australia. She was at ANU and had an offer from Melbourne to do her graduate studies. Remember, Australia is 6 months off on the academic calendar than we are, so when she heard from Harvard, she said, I'm off for Cambridge, which we're glad she decided to do. She was a presidential early career, has a presidential early career award for scientists and engineers, Fermilab Distinguished Scholar, Buchner Special Teaching Award at MIT, John Bacall Fellowship, many other things. I won't keep reading. You can see the list is actually relatively dense. But she is now a professor, associate professor at MIT in physics, and gave a wonderful lunchtime talk. And now we're going to hear about an area of the galaxy that many of us are very interested in. So, Tracy, take it away.
Thanks very much. And that sounds like my mic is unmuted, so very good. Okay, thanks very much for the invitation. I'm very happy to be back here. It's always nice to visit the CFA. And, especially since it's so close. So yeah, I want to tell you today about a sort of ongoing controversy and puzzle, which is sometimes called the Galactic Center GammaRay Excess. This is something that was first discovered around the same time as the discovery of the Fermi Bubbles back in 2009, and my view of its likely origins has oscillated somewhat over the years. But I think whatever it is, it's pretty interesting. So I want to try to convince you of that fact, tell you about what the possible explanations are, and explain the controversy and where we stand now. So I want to begin by just giving some background of where we think. So this is a gamma ray signal. So I'm going to explain where we think most of the gamma rays in the Milky Way come from, what we expect the backgrounds to any search to look like. And then I want to talk about the excess, which is what you see when you start to look in the region of the Galactic Center in a galaxy. I should say I know Galactic Center means different things to different people. Some people here may be using a much more stringent definition than I am. This excess actually fills the region within about 10 degrees of the Galactic Center. So it is the Galactic Center excess broadly defined. I want to talk a bit about the history of the excess, the properties that it has, and the possible interpretations. And this is why this signal has been of great interest to both the particle physics communities and the astrophysics community, because as I'll explain, it has a lot of properties in common with what we might expect from a signal of colliding and annihilating dark matter particles. Now, if that was the case, it would be extremely exciting. It would revolutionize our understanding of physics. But there's another candidate explanation, which for most of the period since the excess's discovery has probably been in the ascendancy, which is that what we could be looking at is the first signs of a new population of pulsars in the galactic bulge. So that would also be pretty interesting if we could confirm it. So I wanted to talk about the methods that my collaborators and I devised a few years ago to try to tell the difference between these scenarios just directly from the data. We developed a new statistical test to try to distinguish these, and we found when we first did that test that there appeared to be pretty strong evidence that the excess was made up entirely of point sources. But then the latest twist in this story from the last year or so is that we've found that there may actually be some pretty significant systematics affecting the original outcome of that test, and maybe dark matter or some other diffuse component is back in the game as a possible explanation after all. So I'm telling you about a controversy. At the end of this, my conclusion is not going to be, therefore it is clearly dark matter, or therefore it is clearly point sources. This is a developing story, and I just hope to bring you up to date with where we are now, and of course get your thoughts on how we might proceed.
You'll come back and tell us the resolution.
Yeah, right. Yes, when we know, if we know in a few years, then I would be very happy to come back and tell you the final answer. Or maybe one of you guys in the audience will figure out the answer, and then you can come down to MIT and tell us. So, yeah, and please feel free to ask questions as I go. Okay, so let me first talk about just what we expected to see when we looked at the Milky Way in gamma rays. So the dominant gamma ray production mechanism in the Milky Way comes from charged cosmic rays interacting with the gas. NASA made this pretty simulation for us back when I was a student here. If we have a cosmic ray proton that comes in and strikes a hydrogen atom in the interstellar gas, that can produce that will produce a number of particles, including pions. Neutral pions decay 99% of the time into gamma rays. And this is the main mechanism by which gamma rays are produced in the Milky Way. Because this comes from a bath of charged cosmic ray protons interacting with the gas, the expected signal traces the gas density in the galaxy. So this is just a map of the interstellar medium. I think this is actually a dust map, which is a pretty good tracer of the gas. We expect that the bath of charged protons is roughly uniform throughout the galaxy, just because protons propagate around the galaxy many, many times before they lose their energy. They're just diffusing through the galaxy's magnetic fields. So to a first approximation, we expect the gamma ray sky to look like the map of the gas in the galaxy. We have other sources of gamma rays as well. In the diffuse emission category, same as what we just talked about, you can have other kinds of cosmic ray interactions with the gas and the starlight. When cosmic ray electrons upscatter ambient photons, they can upscatter them up to gamma ray energies. So that gives us a signal that depends on the cosmic ray electron density and on how the starlight's distributed through the galaxy. Likewise, when those cosmic ray electrons scatter off the gas, they can produce bremsstrahlung photons, and those can also show up in the gamma ray band. So then this will depend on the electron density and on the gas map. Now, then we come to other contributions. So in principle, we know that 80% of the matter in the universe is dark matter. In some models of dark matter particles colliding could produce visible particles, or dark matter decaying away could produce visible particles. I'll say more about what these signals look like later, but in principle, this could also produce high-energy photons or high-energy charged particles, which then produce photons through the mechanisms that we just discussed. We also have some compact point sources of gamma rays. The Fermi Gamma Ray Space Telescope has found several thousand gamma ray point sources in the galaxy. The galactic sources, for example, include pulsars and supernova eminence, and there are also extragalactic sources, of which the main category is active galactic nuclei of some kind. So we expect our gamma ray sky to be a superposition of these various components with a question mark on this one, because that's the one that we don't know if it's actually happening. So if we leave aside the point sources for the moment and just try to make a model of what we expect the diffuse gamma ray emission to look like, it looks something like this. This is just a model built by, I think this is a simple model that we built back when I was a grad student at Harvard, constructed from a map of the gas, plus estimates of where the radiation is and where the cosmic ray populations are, and I can change the saturation scale. So all I want you to take away from this really is that the backgrounds are brightest along the galactic plane, where all the gas is and all the stars are, but there's significant residual emission at higher and lower latitudes, mostly tracing the gas map. Okay, so that's what we expected to see, that plus some collection of point sources. So what did we actually see when we got the gamma ray data? So this happened back when I was a PhD student here at CFA. The Fermi Gamma Ray Space Telescope was launched from Cape Canaveral in June 2008, so it's been up there for 11 years now. It's still taking data. It will keep taking data until they decide to defund it. So it's in low Earth orbit. It has a 90-minute orbit, and it scans the entire sky every 2 hours. I've written here it's sensitive to gamma rays from 300 MeV up to several TeV. It can actually go to lower energy than that, just the performance of the instrument starts to degrade. And all the data is public, so I am not a member of the Fermi collaboration. All the data that I show you, basically all the data I show you in this talk is going to be from Fermi, so I'm grateful to the Fermi collaboration for making their data public and accessible. Okay, so back when I was a student here, and Doug Finkbeiner and I and the other members of our research group, including my colleague Meng Su, pulled the data in 2009 when it first became public. This is what the data looked like as of 2010. The point sources have been subtracted from this data. These white regions are just regions where there was a very bright point source and the residual is large, and so it's been masked out. Okay, so if you know what you're looking for, you can actually already see, so this is my data minus model, but so far this is just the data, you can actually see that there's stuff in this data that was not in the model that I sketched for you on the previous slide. If you don't know what you're looking for, it's a little bit harder though, so we can subtract the that model from the data, look at the residuals, and what you see is something that looked like this. And again, this was circa 2010. This was 2 years of data, as we have quite a lot more of it now. But you can see already in this these figure-8 shaped structures. These are the structures called the Fermi Bubbles, which were first described by Meng-Su and Doug and myself back in 2010. This was basically the last thing that I did in my PhD. Before leaving Harvard, it was a good note to go out on. And so what are these objects? So despite 10 years of study, these are also a mystery, and I could give a separate colloquium on those, but I won't today because I think people here can always talk to Doug about them. So this is a colored version of the same image that we have. The Fermi bubbles are these giant figure-8 shaped structures. They appear to be centered at the galactic center, but they extend about 50 degrees to the north and south. They're bright in gamma rays between about 1 and 100 GeV, and we see counterparts in X-ray and in microwave. In terms of where they originate from, they may be a relic of activity of the black hole at the center of our galaxy, or of many supernovae going off in the inner galaxy. Since we first discovered this, there has been some extra observations that indicate that there is an outflow in the base of the bubbles with a characteristic speed of something like 1,000 kilometers per second. So there's some transport of material from the galactic center out to the outskirts of those bubbles. And that suggests a characteristic age of a few million years out to about 10 million years. That said, there are still a number of puzzling features of the bubbles and their origin. It's still an open question. But the puzzle that I want to talk to you about, that I want to focus on today, is a different one, which is what happens when, instead of looking at these large bubble structures, we look in at the inner galaxy region right around the galactic center. So I'm going to now zoom in to here. At the same time that my colleagues and I were looking at this data and extracting the Fermi bubbles, there was another pair of scientists, Dan Hooper and Lisa Goodenough, who were looking at the region around the galactic center, and they said, if we do the same kind of exercise, subtracting off the background model, then we see what appears to be an extended excess around the center of the galaxy. So this is from a paper from around this time, a little bit later, sketching the spatial morphology of the excess. So this is a map of all the photons in a 7 by 7 degree region around the galactic center after point models for the known point sources have been subtracted. And then once we subtract off our best estimate of the diffuse background coming from cosmic rays interacting with the gas and starlight, then what you're left with is this blob. I should note the color bars from left to right here are different by a factor of 3. So this is not 100% of the emission. It's more like 20 or 30% of the emission. But it's not a tiny signal. So this blob is roughly spherical. And from this plot, you look at it and you say, okay, this is isolated to the region within a degree or so of the galactic center. In this first discovery, they also you can measure the energy spectrum of this excess. And what they found was that the peak of the excess occurred at about 1 or 2 GeV, and then measured in, so if I measured the emission in power per logarithmic interval, so E squared dNdE, then there was a peak at 1 to 3 GeV, and then it dropped off both at lower and higher energies. Now, and this is from an analysis in 2013. The red points were statistical errors, and the black points were meant to be like a first estimate of the systematic uncertainties. There are other lines on this plot, which is why the particle physics community got excited. But so these are still the basic features of the excess. They were first noted in 2009. They're still pretty robust 10 years later, that it has a bump-like spectrum, peak at 1 to 3 GeV, and a morphology that is at least a lot more spherical than it is disk-like. So when I got involved in this story was in 2013, where we found that while on this plot you might say this looks like it's confined to the region within a degree of the galactic center, it actually extends into the inner galaxy to about 10 degrees away from the galactic center. But as you might infer from this, it's pretty steeply peaked towards the galactic center. It falls off quite rapidly. And the Fermi collaboration also eventually did confirm that this excess is there in an analysis in 2016. So we can say a little bit more about the properties. So my collaborators and I, in a paper that we posted in 2014 and got delayed in publication, so eventually came out in 2016, we found that the photons peaked consistently around 1 to 3 GeV in energy everywhere in the excess. So if you looked at the galactic center or you looked 10 degrees away from the galactic center, the spectrum looked extremely similar. We found that this excess was approximately spherically symmetric. It was steeply peaked at the galactic center. There have been subsequent studies that showed that you can also describe it as a centrally symmetric core, but then outskirts that look more like the stellar bulge of the galaxy. So that's more box-shaped than spherical. So the robust statement is that it doesn't look like the disk, but trying to distinguish something that looks like the bulge versus something that looks really spherical is more uncertain and depends more strongly on how you model those complicated backgrounds from cosmic rays interacting with the gas and starlight. These are plots taken from a paper by Colore, Hollis, and Weniger in 2014, which demonstrates what I mean by spherical symmetry. So what they did was they subdivided the excess into these different subregions marked on this plot, and this is the spectrum for the excess that they measured independently in each of these subregions. Black points are statistical error bars, the yellow bands are an estimate of systematics, and you see that pretty much in all of these regions, so inside the Fermi Bubbles region, outside the Fermi Bubble region, towards the galactic center, further out from the galactic center, you see the same kind of structure with a bump at 1 or 2 or 3 GeV. Although, so the outermost regions here are 15 to 20 degrees and more than 20 degrees away from the galactic center. And at that point, there's maybe still a hint of the bump, but the statistical significance is not very high. So this appears to be a pretty pervasive, pretty consistent spectrum feature of the whole inner galaxy region within 10 degrees from the galactic center, which is about 1.5 kiloparsecs or about 5,000 light years. Okay. Is that a question, or did you have a question?
No, just that you had Roman numeral 11.
Yes.
I think you should have had 9.
Yes, yes, I mean, well, I'm not an author, I'm not a co-author on this paper, so I will blame them. But yes, I agree, it should be 9, not 11. So what could this excess be? So what could this excess be? Well, the possibility that makes particle physicists happy, and I'll explain why particle physicists like this idea so much coming up shortly, is that this could be coming from dark matter particles colliding, producing visible particles. This would be our first detection ever of non-gravitational interactions between dark matter and the standard model. If confirmed, it would be super exciting. But of course, there is a possibility that it's, what particle physicists call conventional astrophysics, i.e. any astrophysics that doesn't actually involve modifying the standard model of particle physics. So the leading explanation, I'm both a particle physicist and astrophysicist, so I can tease one half of my, I can tease my colleagues. So the leading astrophysical possibilities, well, one is that what we're looking at is a new population of point sources. The leading explanation for that is even already shown in this plot from 2014. So this is again the spectrum of the excess. These black points are the data with statistical errors only. This black line is a best fit dark matter model, so this has been fitted to the data. But the dashed lines are observations of either globular clusters, which have gamma-ray emission that's thought to be dominated by millisecond pulsars, or one of these lines is the stacked emission of all gamma-ray millisecond pulsars found by Fermi. And you see that these lines are not very different from the data points. In particular, the high energy cutoff looks extremely similar. The low energy band looks pretty different, but if I were to put systematic error bars on this plot, the systematic errors would be largest at low energies because that's where Fermi's energy resolution and angular resolution both start to degrade. So the spectrum of the excess that we see is pretty consistent to what we would have expected from millisecond pulsars. So that is the most discussed candidate for the excess if we're looking at some new source population, although it could be something else. The other possibility, if we're sticking to conventional astrophysics here, just from the list of gamma ray sources that I gave you before, is maybe we're looking at some kind of new diffuse background. Maybe there was some outflow or burst from the galactic center, maybe that produced a lot of extra cosmic rays, and through interactions with the gas and starlight, it could make this signal. And in some sense, this seems very natural because we know there was an outflow from the galactic center because we see the Fermi bubbles. However, for various reasons, I think that this is a less enticing explanation. Partly, the spectrum of the excess is very constant across the excess. It's the same at the galactic center or further out from the galactic center. And the emission that we see, so that makes it difficult to explain by electrons, which as they propagate out from the galactic center should be losing energy. So if it was electron scattering on the starlight, you would expect the spectrum to have a gradient. With distance from the galactic center, we don't see that. If it was coming from charged cosmic rays scattering on the gas, we would expect to see a correlation with the gas. We don't see that. So the combination of the morphology and the very consistent spectrum incline me towards thinking about one of these two explanations as opposed to the diffuse background explanation. So from here on in the talk, I'm going to pretend like the two explanations we're trying to distinguish are dark matter annihilation versus a population of point sources, but I can say more about the possibility of it being some other diffuse outflow if people are interested. And so yeah, when I say dark matter from here on in, I'm mostly just going to mean something that is smooth and diffuse and not made of point sources. Okay, so let me just say a little bit about why, what those two hypotheses explain. So dark matter is what I spend the vast majority of my time thinking about. So here's the 1 minute summary. Dark matter is somewhat more than 80% of the matter in the universe by mass. By dark, we mean that it has no electric charge, or at most a very tiny electric charge, and that it interacts at most pretty weakly with the known particles. We have many lines of evidence for that statement. This is in some ways a very surprising statement, but from rotation curves in galaxies, from gravitational lensing of colliding galaxy clusters, from the imprints left on the CMB and the formation of galaxies, we have pretty good reason to believe that this is true. But we've only ever detected dark matter by its gravitational interactions, and that's not enough to really narrow down its identity. For example, the possible mass range for dark matter candidates ranges from something like 10 to the minus 21 eV up to something in the size of asteroids. So there's an enormous range. What we know is already enough to tell us that with the possible exception of very tiny primordial black holes, there are no good candidates in the physics that we already understand. So this is one of our biggest clues to what might lie beyond that known physics. And if we want to figure out what it is, there are some models where we might be able to get an answer just by looking at the distribution of dark matter. But if we could see a non-gravitational interaction between dark and visible matter, that would be an enormous step forward in our understanding of this component. So, what kind of signals might we look for? Well, a classic example that people think about is the possibility of dark matter annihilation. This is like matter-antimatter annihilation. If two dark matter particles collide, and then a miracle occurs, this is the new physics that we would like to probe, then visible particles could potentially be produced. Now, most visible particles that we could make are unstable, so in general, the unstable ones will decay. The signal that we'll see in the end is an ensemble, a spectrum of the long-lived known particles. So these could be photons, neutrinos, electrons, protons, and their antiparticles. So furthermore, if this process occurs, then it could potentially explain why we see the abundance of dark matter that we observe. One explanation for the observed abundance is that there was a lot more dark matter in the early universe, but most of it annihilated away, so it was depleted by this exact process. That is not guaranteed in all dark matter models, but is one possible explanation. If that is the case, then by looking at the observed amount of dark matter today, we can infer what this annihilation rate had to be. When you do this calculation, you find that it gives you a pretty mass-dependent prediction for the required cross-section, which is about 2 to 3 times 10 to the minus 26 centimeters cubed per second. If we translate that into particle physicist units, that corresponds to a mass scale of about 100 GeV if the interaction had a coupling comparable to the weak interaction. And this second equality is sometimes called the WIMP miracle, that you naturally get the right annihilation cross-section from weak scale physics. But the first equality here is just a statement about this is what you need to get the right abundance of dark matter at late times. It doesn't have any particle physics assumptions. Okay, so we might want to look for photons or neutrinos or charged particles being produced from regions of the galaxy or the universe where we think there might be large dark matter densities. And if we found such a signal and it lined up with this cross-section, then we would simultaneously have an explanation. Then if it was dark matter, we would simultaneously have an explanation for why dark matter has the abundance that it does. What other features can we look for in a possible dark matter signal beyond that rate? Well, we can look at spatial information and spectral information. So for spatial information, as I said, the backgrounds in gamma rays look like this, more or less. They're brightest near the galactic plane, but we know from rotation curves that dark matter is in a large halo around our galaxy. We expect it to be roughly spherical in the inner regions. So the signal here should trace the dark matter halo. Regions of higher dark matter density have more signal, and so we would expect it to look more spherical as opposed to tracing the galactic disk. As far as spectral information goes, many of the backgrounds that we can look at from charged particles interacting with the gas give rise to mostly power law-like spectrum, whereas the signal, it has a characteristic scale that is set by the mass of the dark matter particle. That's the characteristic energy scale, so you expect some kind of bump or peak with the scale determined by the dark matter mass. If you ask, where do we expect the signal to be brightest? It's usually in the galactic center. That we think is the biggest local concentration of dark matter. But of course, the backgrounds are also most challenging there. The prescription that we're going to use for modeling that we use for modeling the dark matter density in the galactic center, because we don't really know how steeply the density rises towards the galactic center. We just parameterize with this form. This is called a generalized Navarro-Frank-White profile. RS here is the scale radius of the Milky Way. It's about 20 kiloparsecs. For purposes of looking close to the galactic center, this denominator term is basically irrelevant. So we're essentially just modeling the signal as with the power law dependence on galactocentric radius. The galactic center excess is reasonably well described by that. The power law that you would need for the dark matter density, if this was really a dark matter annihilation signal, is about r to the minus 1.25. And the signal scale is like the square of that, which is r to the minus 2.5. So dark matter, so if this is the explanation, this naturally gives you the fact that the spectrum is the same everywhere that you look in the excess, because the spectrum is just being set by the mass of the dark matter and what it annihilates to. It naturally gives you the fact that the signal has a roughly spherical morphology. The fact that the signal is steeply peaked at the galactic center, that can be accommodated within dark matter simulations, although it's not a clean prediction because it depends a lot on what the baryonic physics is doing in that region. And perhaps most interestingly, the rate that you need, the annihilation rate that you need to match the signal, actually lines up extremely well with that thermal relic rate. It's 2 to 3 times 10 to the minus 26 centimeters cubed per second. So these factors are why this excess got a lot of particle physicists extremely excited about the possibility that this might be the first signal of dark matter annihilation that we've seen. On the other hand, as I said, the competing explanation is pulsars. So pulsars are rapidly rotating neutron stars that emit, so they can emit a beam of radiation. As they spin, they can emit over a wide range of wavelengths. For this excess, we'll be particularly interested in millisecond pulsars, which are those with very short millisecond periods. The main way that we know to produce millisecond pulsars is that they're an old pulsar that is then spun back up by accretion from a partner. So they occur in binary systems, which means that we expect them to have a large abundance in regions of very high density, which could explain why we see this signal dominantly from the galactic center, not from other areas. So what do pulsars get you? Well, as I said earlier, this is the big argument in favor of pulsars. The spectrum of the observed millisecond pulsars matches the excess really well at energies above 1 GeV. And like, that's not a fit, that's not a model, that's just compare the excess to the observed spectrum. These scenarios can probably accommodate the observed morphology, which is not quite the same as predicting it. As I said, these MSPs originate from binary systems, so it's reasonable that they could be brighter in high density regions. If you want a spherical distribution for the millisecond pulsars, there are some mechanisms to possibly give that. As I mentioned earlier, there have been some recent studies that say that maybe the outskirts of the morphology of the excess look more like the stellar bulge rather than something spherical. If you can, I think that is not especially robust at the moment, but if you could confirm that robustly, then it would strongly support having some kind of stellar population generating this excess. Okay, so those are the prior to 2015 arguments about whether this should be dark matter or pulsars. In 2015, my collaborators and I decided to try to do a better job of distinguishing hypotheses, and since this is about a dark side versus light side explanation, I'm going to frame this in terms of Star Wars metaphors. So in the pulsar wars, there was a major development in 2015, which that we developed a new statistical technique to try to tell the difference between the dark matter hypothesis on one hand and the pulsar hypothesis on the other hand. Okay, so I want to go into that, but I guess I'll just pause and ask if anyone has any immediate questions before I tell you what we did. Okay, very good. So, the first movie. So, back in 2015, my collaborators and I said, okay, you can spend a lot of time, and there are hundreds of papers debating, is it easier to make a dark matter model that explains this signal or to come up with a pulsar production model that explains this signal? And I'm glad that people did that work, but we wanted to go back to the data and see, could the data on its own tell us which of these was true? In particular, if we were looking at dark matter or any other diffuse origin for the excess, then what we would expect to see is a fairly smooth signal where the variations from pixel to pixel come from Poisson fluctuations. Okay? Every line of sight towards the galactic center would have dark matter particles along it. On the other hand, if what we're looking at is a population of compact sources, then you might hope to see hotspots and cold spots in the excess that correspond to regions where there are sources and regions where there are not sources. Now, of course, in the extreme limit, this would be very easy to see. If the Galactic Center excess was coming from 5 bright sources, then we would have just identified the 5 bright sources and we would not be having this conversation. However, if it's coming from thousands of faint sources that could not individually be identified as sources, you might still be able to see a higher than expected level of fluctuations, which would tell you about the properties of this population. So the idea was basically just to look at the clumpiness of the signal. There was a related analysis at the same time using a wavelet approach just to try to study how much small scale power there was in this inner galaxy region, which is sort of another way of getting at a similar question. So just as an example of how the statistics work here, suppose I tell you that my model predicts that there should be 10 photons per pixel in this region of the sky. And I ask you, what is my probability of finding 0 photons or 12 photons or 100 photons? Now, the first thing, if I tell you this with no further information, you might assume that I mean, okay, let's assume that photon events are uncorrelated. Let's assume that, seeing one photon from a pixel doesn't tell me anything new about the pixel. Then I can use Poisson statistics. And I find that the probability of seeing 12 photons is about 10%, the probability of seeing 0 photons is a few times 10 to the minus 5, and the probability of seeing 100 photons is completely negligible. It should just never happen, unless I have 10 to the 63 pixels in my image, which I do not. So, but then I say, okay, I'm going to give you some extra information, which is when I said I expected 10 photons per pixel, what I actually meant was I expect that there's a population of sources in this region that produce on average 100 photons each, but I only expect to see one of them in a pixel one time in 10. So that still has the same expected mean number of photons. If I average over many pixels, I will get the same photon flux from both cases. But now my probability of seeing 0 photons is not a few times 10 to the minus 5, it's 90%, because that's my probability that I just don't have a source in this region. On the other hand, my probability of seeing 12 photons is now extremely tiny, because first I need to get a source in this region, and then it has to fluctuate down from 100 photons to 10 photons, which is like a 9 sigma fluctuation. So you get like a 10 to the minus 29 probability. My probability of seeing 100 photons, on the other hand, is now quite good. Actually, it's a few times 10 to the minus 3. So if I'm comparing these two hypotheses, and I look at a handful of pixels in both cases, if I see any pixel with 100 photons, case 2 is going to be very strongly favored over case 1. And if I see any pixel with 12 photons, then case 1 is going to be very strongly favored over case 2. So essentially, case 2 has higher variance. You don't need to just compare means. You can also look at the variance of the data compared to the variance expected from your model. Okay, so the way that we implemented this idea was to say, okay, we're going to model the sky as a linear combination of different components, and these components may have associated statistics, associated likelihoods, that are either Poissonian or have this distinctive point source-like statistics. So the templates that we use for the smooth emission are a model of the diffuse emission, which is similar to what I showed you earlier, a simple model of the Fermi Bubbles, which I also mentioned to you earlier, a model of isotropic emission, so this is just gamma rays produced in other galaxies, produced across the sky, and a signal template. So the signal template, I mean, it's modeled on a dark matter model, but it's really something that has been adjusted to give a pretty good description of the Galactic Center excess. Like, this is not an a priori prediction of a dark matter simulation or anything, this is just a fit to the Galactic Center excess. Then we're also going to include models for point source populations that are on one hand isotropic, so this would represent point sources in other galaxies. We're going to consider populations of point sources that trace the disk of the Milky Way, because we know that there are stars and pulsars and supernova eminence in the Milky Way's disk. And again, and in some of our fits, we're going to test the possibility of a population of point sources that has the spatial distribution of the Galactic Center excess. So the distinction between this signal template here and this signal template here, their spatial distributions are identical. The only thing that's different is their statistics, is their probability of data given model. So when I model the sky as a linear combination of these objects, each of these diffuse models have one parameter associated with them, which is their overall normalization. Each of these point source templates has 4 parameters associated with them. One describes the overall normalization. The other 3 describe how many sources I have as a function of the flux in the sources, which we model as a broken power law. You could choose a different modeling there. We checked a couple of different options. So then we can compute the probability of getting our observed data given this model. So the probability of getting the observed data as a function of this set of parameters. then we can either do a frequentist analysis where we maximize that, so we multiply together these probabilities for all the separate pixels. We can either maximize that likelihood and do a frequentist analysis, or we can use that likelihood to derive posterior probability distributions for all of the parameters associated with these templates. Okay, so we're doing a likelihood analysis. It's just that the P that we put in depends on whether we're modeling the signal as smooth emission or as a bunch of point sources. Okay, does that make sense? Because this is the, it's important to understand this bit. So what are the results that you find? What are the results that we found back in 2015 to 2016 when we did this? So we restricted this analysis to the region within 30 degrees of the galactic center, and we masked out the galactic plane at plus or minus 2 degrees. And then so the first thing we wanted to do is expressed in this inlay. So we wanted to fit for the, we wanted to do a fit where the signal, the galactic center excess, is only modeled by a smooth component. So there's no option to have it be described by point sources. So this is like the baseline. This is the kind of analyses that people have done before. This plot is a plot of the posterior probability distribution for each of these templates to have a certain fraction of the flux in this region associated with it. So if we look at this inlay first, the red line is the smooth galactic center excess template, which is labeled here as NFWDM. And what we see is that the posterior for this component, for this template, is peaked around 7% of the total flux. So in this 30-degree region, that corresponds to the fitters assigning about 7% of the total flux to the galactic center excess. That's consistent with the normalizations in previous studies. I said earlier it was a 20 or 30% signal, but that's at the galactic center. If you average over a larger region, then it goes down. Okay, but so now what happens if you include a template that corresponds to the galactic center excess spatially, but is now allowed to have the statistics of a point source population? So that's the larger plot here. The red line is, again, the smooth contribution to the excess, the smooth component, and the yellow line is the point source contribution to the excess, so the new template that we've added into our fit. And you see that in this case, the smooth component picks up 0 coefficient, and the point source contribution to the excess peaks at about 7 or 8% of the total emission in this region, i.e. 100% of the excess. Okay? So, and the nominal significance for there to be point source, for this signal template point sources, the fit including this template versus the fit excluding it, is preferred with a Bayes factor of about 10 to the 9. So it's, so it looks on statistical uncertainties only, at least there's a very strong preference for point sources. So the 0th order result of that analysis is here. If you're a particle theorist who wanted to explain this with your favorite dark matter model, you are probably sad. If you're an astrophysicist saying, aha, we have discovered a new population of gamma-ray point sources in this region, then you are happy. But, okay, so we can say a little bit more about results of this. As I said, we marginalize over the parameters, including the parameters that describe the source count function of the excess. So this plot shows the posterior distributions for the source count functions associated with the blue line is for point sources associated with the disk of our galaxy, and the orange band is for point sources associated with the excess. So for the disk, we find this pretty straightforward power law-like luminosity function, which is consistent with what we expected. For the excess, our best fit source count function has a very steep cutoff, right around where Fermi starts to lose sensitivity to point sources. These black points show the number of point sources detected by Fermi, and so you can see that around here you're just starting to lose the ability to find them. So the result from 2015 was that at this point you expect there to be this large population of sources lurking just below the threshold, which contribute the bulk of the galactic center excess. This best fit source count function has a lot of power at the high flux end. This is dNdF, and very little power at the low flux end. So with this best fit, we found that you could explain half the excess with only about 100 sources, which were all pretty bright. And the full excess you needed, with this source count function for the full excess, you needed less than 1,000 sources because there just weren't very many faint point sources. Okay, so this analysis suggested in 2015 that there was a lurking population of bright sources just below Fermi's sensitivity threshold, and that was explaining the bulk of the excess. Okay, so now I want to go to episode 2, which is the updates from the last year or so. So this paper has just been published in PRL, just came out this week. Okay, so if that story sounded convincing to you, then good, because it sounded convincing to me as well for most of the last 4 years. But last year, Rebecca Lean, who's an excellent MIT postdoc, came to me and said, I would like to know how to work with Fermi data. And I said, okay, let's, well, this analysis was pretty important, but most of the checks on systematics in this analysis are basically the checks that we did in the appendix of the 2015 paper. Like there hadn't been a whole lot of follow-up studies on this. So I said, okay, let's go back and try to, hit the method with a hammer a little bit and understand under what circumstances would it break. Under what circumstances could this method that we applied tell us that the excess was 100% point sources when in fact that was not true? In particular, can we find cases where that would happen, where the excess was dominantly from some smooth component, and thus the result was wrong? So back in 2015, we had, of course, been worried about this issue already, because we know that our modeling of the diffuse emission is not perfect. Like, our modeling of the diffuse emission relies on estimates for where the charged cosmic rays are in the galaxy and where all the starlight is and where the gas is in 3 dimensions. And we don't know any of these to the level of accuracy needed to fully explain the GammaRay data. Okay, so you always have to worry about what are the possible systematics from messing with the diffuse model. So back in 2015, we'd done a number of tests. We tested this method in other regions where there were discrepancies between the model and the data, and tested that in those cases we didn't find a strong preference for point sources. So it wasn't like our method was just returning point sources absolutely everywhere. That was special to the Galactic Center. That said, the caveat on this is that there is some reason to believe that our gas models are worse in the Galactic Center than they are everywhere else. So it is kind of a special region. We tested the method in mock data that was built with one diffuse model and fitted with a different one, and we found that it didn't really bias the preference of point sources, although all the models that we tested were built using the same underlying gas maps. We tried dividing the excess into different spatial regions with which have pretty different diffuse emission, and we found consistent properties for the point source population in all of these regions. So those, we tested, we were pretty happy with these tests. As I mentioned, there was also a wavelet-based study in 2016 which did find evidence for small-scale power in the region of the Galactic Center excess that was beyond the expectations from the diffuse background. So that at least suggested that there were some sub-threshold point sources in this region. Of course, the question then becomes, do those sub-threshold point sources have anything to do with the Galactic Center excess? So one question that we wanted to ask was, suppose there were point sources in this region, but they just don't really have much to do with the Galactic Center excess. They're associated with the disk of the galaxy or the galactic bulge or with the Fermi bubbles. Could that give you if you failed to include those extra populations in your fit, how badly could that bias the posterior for the smooth component of the excess? So this is a test that, so the idea that we had was, maybe you could have suppose there was some new point source population present that wasn't well described by the templates in our fit. So it wasn't described by point sources along the disk of the galaxy plus point sources in other galaxies. One possibility for this might be, there had been some studies looking at the base of the Fermi bubbles that had found there was evidence for small dense gas clouds in the low latitude part of the Fermi bubbles. And since the Fermi bubbles, we believe, are full of high energy cosmic rays that are making the high energy gamma rays, when those cosmic rays hit the gas, they could potentially light up those faint gas clouds in gamma rays. Fermi's angular resolution is about 0.1 degree to 1 degree. So anything more concentrated than that looks like a point source from Fermi's perspective. So we said, okay, just hypothetically, if you had a bunch of point sources in the base of the bubbles, and you tried to run the fit that we ran in 2015, which doesn't have a model for those point sources, what would happen? Because in principle, what might happen is that we're trying to fit the point source in the sky with this combination of templates. The disk point sources are basically orthogonal to the Fermi bubbles. The isotropic point sources, if you modify their brightness in the center, you have to modify it everywhere in the sky. So the easiest way to pick up these point sources might be to drive up the normalization of the GC excess point source template. And if that happened, well, then we would be predicting way too much flux in the center of the galaxy, but we could compensate for that by driving the smooth component downwards. So that seemed like a plausible way that you might get biases. I'm just going to give you a preview and say we have tested the data for, are there gamma ray point sources in the base of the bubbles, and we don't see them. So this is a hypothetical example. This is a proof of principle. This is not exactly what we think is going on in the real data. But we do think that something is going wrong in the real data. So if we But if we look at this example in mock data, so we simulate data where we construct a mock data set using all the standard templates, except that we assume that the galactic center excess is completely smooth. So we simulate a smooth galactic center excess signal, and we add a component which is point sources that are spatially correlated with the Fermi bubbles. And then we rerun the analysis that we did in 2015. And we see what happens. So the truth value here is that, so this is in a somewhat different region to what this is normalized to a different region than what we saw in 2015. The fitting region is actually the same. The normalization region is larger because we took a slightly non-obvious choice in 2015. But so the expected size of the galactic center excess in this region is about 2% of the total photons. So when we fit with all the correct templates, we're injecting, then we recover the correct amount of dark matter that we simulated, which is about 2% of the total, and we recover our bubbles point source population, which has a similar overall normalization and flux in this case. But now, if we rerun the fit that we did in 2015, which is incorrect in that it doesn't have a template for the bubbles point sources, then what we find is what we might have expected, that we find a preference that the excess is 100% point sources. This NFW point source signal goes up to absorb the full excess, and the smooth dark matter component gets reconstructed at 0, even though in reality it was 100% of the excess in the simulated data. Okay, so that's consistent with the behavior observed in real data. So the summary from mock data is just, whenever you do a template analysis, if you use the wrong templates, you can get the wrong answer. I mean, this is just a basic feature of template fitting. So if the templates don't adequately describe the data, the template coefficients will in general be biased. Point sources spatially correlated with the Fermi bubbles give you an existence proof of a case where if there was a point source population in this region, it would give you a large negative bias in the template coefficient for any smooth component, explaining the excess. So it's a proof of principle example of a situation where the mock data in this case contains a dark matter signal or a smooth signal, if you don't like dark matter but you like cosmic rays, comprising 100% of the excess, but the fit concludes that there's basically no smooth component to the excess because it's trying to explain an unmodeled set of point sources. So, does this occur in real data? Part 1 is, okay, let's just put in a model for the Fermi bubbles point sources and just double check that it's not literally the Fermi bubbles that is screwing this up. It turns out it's not. We put in a template for bubbles correlated point sources. The fit gives it a 0 coefficient and still prefers to assign the galactic center excess flux to point sources. So that's fine. But then you might say, okay, but this doesn't really answer my question, which is, could there be a population of point sources in this region which is messing up the fit? So there are a few different ways to get at this question, but what we ended up doing for the first paper was an alternative test suggested by Tim Linden, which doesn't give us as much information on exactly what is causing problems, but just tests for, are there problems in the fit? Full stop. So the idea here was just to add a simulated smooth dark matter signal that looks like the excess on top of the real data, and then run the pipeline and see if we can get it back out. If the kind of bias that we just described was present, then there's no particular reason for that bias to be saturated at setting the dark matter component to 0 and the excess that's present in the real data to 100% point sources. We could make the excess twice as large, and you would expect that at least some of that could also be absorbed by the bias. So that's the test that we're going to do. So first we're going to just test So first we're going to test a couple of different cases. So first, let's just check that when we inject extra data, an extra signal on top of simulated data where we understand all the components, that we can actually get back what we injected. So let's just check that our method actually works on simulated data. So this is simulated data where you simulate the excess being 100% point sources. And then you say, okay, if we add an extra dark matter component on top of this, can the fit correctly reconstruct it into a point source component that you had originally and the dark matter signal that you injected? So here in each of these plots, the blue lines correspond to the amount of injected dark matter, and the red line corresponds to the amount of reconstructed dark matter. And when you inject an amount of dark matter that's fairly comparable to the excess, you see here it's not getting it quite right. It's biased a bit low. That said, the error bars are pretty large. It's like 1.5 sigma low. As you inject more dark matter, though, as you start injecting signals that are noticeably larger than the galactic center excess, then the fit finds the correct injection. This is just one example realization, but we can do this over a range of realizations. And we see that in general, as you inject more dark matter, the fit will converge and pick up the and correctly reconstruct the amount of smooth emission that you added in. Okay, so that's just checking that things work. So now let's see what happens when we try exactly the same thing on the real data. So this is the fit before we inject any dark matter. This is what I showed you earlier. So the posterior for the point source galactic center excess component is now the purple line. For the smooth component is the red. Before we inject anything, we find that the excess, which is water 2% in this region, is 100% point sources, 0% smooth. That's what we found before. So now we'll inject some extra dark matter and rerun the fit. And you see that the point source component, that the smooth component stays at 0, like pretty conclusively at 0. The sigma here is quite small, unlike in the simulation case. And the point source component jumps up to absorb 100% of what you put in, goes to 4% instead of 2%. We can keep doing this. We can add a dark matter signal that's about 3 times larger than the actual excess. And so in simulations at this point, we were getting the right amount of dark matter back. The smooth component still, in this case, gets reconstructed at 0. And the point sources goes up to 4 times the original size of the excess. If you add a signal that's about 10 times larger than the original size of the excess, then you do finally start reconstructing part of the smooth component. In this case, with big error bars, the normalization's still off. Okay, there's another way to look at this, which is to, rather than injecting extra signal, just say we're going to relax the priors on the original analysis. So in our original analyses, we always require that all components have positive fluxes, because there shouldn't be any absorption in gamma rays, like nothing should be going negative here. But you can still let the coefficient for the smooth component go negative just to see if the fit wants to drive it into an unphysical region. And it turns out that indeed that's what's going on. When we said that the dark matter component was driven to 0, the actual best fit is that the dark matter component is driven to a value that's about -5 times the baseline size of the galactic center excess. So allowing the smooth component to go negative, this is what happens in the real data. The dark matter wants to be at -10%. In simulated data where we simulate the bubbles point sources and a smooth component, then you see like the same behavior, that the smooth component gets pushed to a negative value, but to a much smaller degree. This gets pushed to about -1 times the galactic center excess. And in simulated data where we understand all the templates and all the templates are correct, then you would expect this to be reconstructed correctly, and it is. You allow the dark matter component to go negative, its coefficient gets pushed to just to right around 0. So this is a way of understanding what's going on with the injection test. Because the best fit in the data is actually that the DM wants to go to -5 times the GCE, if I add a fake dark matter signal that is up to 5 times as large as the GCE, it's basically just going to slide this best fit up to smaller negative values. If I impose a prior that it has to be greater than or equal to 0, I'm just going to get 0 every time. Okay, so so the summary from real data is, by adding an extra simulated dark matter signal to the real data, we can test whether it's reconstructed correctly. We find that it isn't in the pipeline from 2015, even when the injected signal is several times larger than the excess itself. So that suggests that there is some kind of bias in the analysis, likely due to getting some combination of our signal and background templates wrong, that could potentially hide a true dark matter signal. And this is not what we see in simulated data where we understand the background. So it's not a deficiency in the statistical method that we are using, which works fine when we understand the templates. It's a problem with the templates. Okay. So that is the main result of our recent paper. So I'll just pause and ask if there are any questions at the moment before I tell you, where do we go next from here. So I should say, what I've shown you has no positive evidence that the excess is made of a smooth component, right? I mean, like, nothing I've shown you suggests that there has to be a smooth component there. It just says that it looks like there's a sufficiently large systematic in the analysis at this point that it's overwhelming your ability to distinguish between a smooth component and a population of point sources.
Is it possible that the Fermi bubbles are just not being included explicitly in the model, although you did refer to them?
I mean, we included them as a diffuse component, but not as a point source component. But we've checked that.
But the shape of that diffuse component.
Yeah, it could be. It could be that mismodeling of the diffuse Fermi. So The Fermi bubbles, the template that we are currently including for the Fermi bubbles is pretty faint towards the galactic center compared to everything else in this region. So if it's like a small perturbation around that, I wouldn't expect it to have a big effect just because everything else is much stronger. Like it'd be more likely for an error in the diffuse component coming from the gas cosmic ray interactions to have a big effect there. But if we've just got the Fermi bubbles totally wrong towards the galactic center and they're really much brighter, then they could be a dominant component that we're not modeling properly. Yeah, so we didn't show it, like in the first paper, the only example we had of how this can go wrong is a case where you get the point source population wrong, but we have follow-up work in a paper that the draft is sitting in my inbox, which shows that actually, yeah, if you mismodel the diffuse components badly enough, then you can get evidence for point sources even when there are no point sources in the fit, like just from getting the diffuse components wrong. So yeah, the Fermi bubbles modeling could be playing a role. Okay, so where do we go next from here? So there are a whole bunch of follow-ups that you can do. It may be that there's a relatively minor correction to this pipeline that fixes the problem. We put out the paper when we did because we had tried about 5 things and none of them had worked, so we figured that it was the right time to outsource it to the rest of the field. But I think that you can do, for example, if you think you could subdivide the signal template and just try to tell, are there some regions of the signal where this over-subtraction effect is worse than in other regions? Are there places where you prefer, where the dark matter wants to go very negative and places where it doesn't? And that's part of our follow-up work, although we find some kind of counterintuitive things. So that's one thing that you can do, like just subdivide into spatial regions and try to figure out where the problem is coming from. We can test other well-motivated models for populations of point sources, like point sources that correspond to some subcomponent of the bulge. So far from the tests we've done, we haven't found something that fixes the problem, but that's something that you can do. We can actually get extra data here. All the data sets that I've been showing you is only using about a quarter of the Fermi data set because we imposed some pretty stringent cuts to try to keep events with the best angular resolution. But there's not a huge difference between the top 1 quartile and the top 3 quartiles in angular resolution. It's just the bottom quartile is really bad. So we can potentially, in our recent work, we're actually including 3 times as much data at the cost of a little bit of angular resolution, but greatly improving the statistics. You can do stuff in mock data that just says, okay, suppose we perturb the diffuse model at different angular scales. How does that change? How does that change what you would reconstruct? Other groups are exploring using that same idea to sort of give the diffuse model extra freedom, allow it to be more data-driven, and see if that can allow you to remove this kind of bias. There are other groups who are exploring systematic biases in the pipeline, even when all the templates are correct. I mean, as I showed you, I don't think that's responsible for what we're seeing, but it's good to understand how the method works. Effects of changing the diffuse model, effects of changing the region of interest. So the goals of these follow-up studies are basically to understand what's causing the problem that we see. Are there ways to mitigate it? And if, these systematics are present, then what can we say about the robustness of the conclusions that we can draw? But there's sort of another strategy that doesn't involve perturbing on this non-Poissonian template fitting method, which is just to say, okay, if we think it still might be point sources close to threshold, can we just go try to find those sources directly? So this is a plot from our 2015 paper where we just made a map of where the hotspots were in the sky that appeared to be driving the preference for point sources, and many of these overlap with known sources in the data, but many of them do not. So you could go after that. If you could really find these sources, you might either be able to see the bright end of the Galactic Center excess point source population popping out, or if you found a population that wasn't distributed like the excess, but also wasn't distributed like the backgrounds we were modeling, then including that in our background modeling could help remove this kind of bias. People here, like Doug's group, have done studies on probabilistic cataloging techniques to try to robustly characterize populations of faint point sources, which might be handy here. And actually just this week, there's been another paper that came out which where we went back and repeated the non-Poissonian template fitting analysis from 2015 to 16, they went back and repeated the wavelet analysis from 2016, which argued that there was a bunch of small-scale power in this region. What they've found now, and they compared it to the latest catalog of gamma-ray point sources from the Fermi collaboration, what they actually found is that now when you go back and look at this, it turns out that that analysis in 2015 was really good at finding the point sources that were about to be categorized by Fermi 4 years later. But in 2015, they essentially attributed all of these wavelet peaks to the galactic center excess and inferred from that that the galactic center excess was mostly point sources. And it turns out that a lot of those sources are now known to be not part of the galactic center excess. So what they found, so this is a map of where their, sorry, this is a bit low resolution. This is a map of where their wavelet peaks are on the sky. They found that of 115 peaks, so this is for high significance in a small scale fluctuation, 107 of them were close to a source in the new Fermi point source catalog. About 40 of those 107 could be members of a population contributing to the galactic center excess, like they're galactic pulsars, or we don't know what they are because we don't know of the counterpart. But the other 60-something are either extragalactic sources or they're associated with something that we are pretty sure cannot be contributing to the excess. So they do two analyses in the paper, which is kind of interesting. One is to say, all right, let's suppose that all 40 of these sources really are contributing to the galactic center excess. What is the total flux in them? That total flux on this plot is the green line. The spectrum of the excess as a whole is, from previous analyses, is the blue line. So the total sum of all these sources is about a factor of 4 to the 5 below the galactic center excess. And once you remove these sources, there basically aren't any wavelet peaks left in the analysis. So this says that for pretty bright, near threshold or now identified sources, they can't be making up more than about 20% of the galactic center excess because there's just not enough flux in them. Like the flux previously associated with the wavelet peaks, a bunch of it is extragalactic sources. It doesn't have anything to do with the excess. The other test that you can do is say, okay, so that is just sort of counting up the total flux in stuff that could potentially still be part of the excess. But the other thing that you can do is just mask all of these sources and rerun the analysis, the study of how bright the excess is, and ask if it went down at all. And that distinction is between the blue line and the orange line. And you can see that masking all of these sources does not really change the inferred spectrum or flux of the excess at all. So what I take from this is that the bulk of the emission in the galactic center excess has to be either diffuse or originating from pretty faint sources. So this goes in the same direction as our dark matter strikes back argument that the strong preference for point sources found in 2015 might actually have just been spurious, like an artifact of mismodeling in the backgrounds. Okay, so what is episode 3 in the pulsar wars? So episode 3 hasn't happened yet, so this is speculative. But if this is a population of pulsars, which it still could be, they would just have to be somewhat fainter than what we originally thought, then the easiest way to confirm, well, maybe not easiest, the most robust way to confirm that is going to be finding the pulsations in radio or in X-ray telescopes. So there was a paper done in 2016 that based on this wavelet analysis, so you might need to rejig it a little bit after the latest analysis, but that estimate found that Meerkat could see tens of pulsars from this population. So this is a telescope in South Africa. They're up and running. Once they do their inner galaxy survey, they could see tens of pulsars from this population, and SKA could potentially see hundreds. So if you want to know, how do you prove that it's millisecond pulsars, I think that is how you prove that it's millisecond pulsars. If you want to prove that it's dark matter, that's a harder problem, and I can talk about that in question. But yeah, so to sum up, the galactic center excess is a pretty robust feature of the central region of the Milky Way. It's gained a lot of interest as either a new population of millisecond pulsars, which would give us insight into how pulsars are produced and distributed in this region, or an exotic signal from annihilating dark matter, which would give us new insights into physics beyond the standard model. If we model the galactic center excess as a linear combination of a population of point sources and a smooth diffuse component, then the earlier results a few years ago found that there was a strong preference for the bulk of the galactic center excess to be attributed to point sources, and that has, so that was strongly in favor of the millisecond pulsar interpretation. However, Rebecca Lean and I have tested that the effect of just injecting an extra smooth signal into the real data, and you find that the pipeline from 2015 cannot reliably recover it. So it may be a bit premature to argue based on those arguments and also based on the wavelet argument, since that has also now been revisited, that the galactic center excess cannot be from a diffuse source, such as dark matter annihilation, due to these photon statistics arguments. So if we want to make that argument, we either need to see the pulsars in another wavelength, or we need to understand these systematics and then fix them and rerun the analysis. So, like I said, I'm not going to give you a conclusive answer to what it is. This is an ongoing puzzle. If you have ideas for how to try to sort it out, short of waiting for SKA to tell us if there are pulsars there, then I'd be very happy to hear them. Thanks very much.
Thank you, Tracy. That's a great summary of a perpetually interesting problem. But I think there is hope. Ramesh?
This excess, you said, is circular?
Roughly, yeah. Like in the outskirts, it might be more boxy, but yeah.
Circular, very steep profile, right out to the minus 2.5 or
Yep.
something. And you also said that this is consistent with millisecond pulsars. That surprised me.
Tilde consistent, yeah. So
It's more like a thickish disk than this.
yeah, good, yeah. So this is. So I said that it could probably be accommodated by millisecond pulsars. So what are the ideas for doing this? So if you believe that the population really just looks like the galactic stellar bulge, with maybe like a galactic nuclear stellar cluster, then then what you were finding is that the galactic bulge stellar population has a big fraction of millisecond pulsars in it. And so at that point, I think you have an open question, which is why does this galactic bulge population have a big density of millisecond pulsars? But I mean, if it does, then whatever dynamics gives you the distribution of stars in the galactic bulge will also give you more or less the correct distribution of millisecond pulsars. So there's that sort of level, like, okay, if it looks like the bulge, then this is just an observational statement about a stellar population. Yeah.
Does the bulge have this very steep profile?
If you look at good. So the people who have written these papers making the argument that it looks like this are using observational data on so the steep component is towards the center of the bulge. They're using observational data on this nuclear stellar cluster and adding that into the bulge component. And they claim that that is consistent with the steepness of the profile. Now, as far as I can tell, there have been a few different papers trying to estimate what the stellar distribution is in the bulge, and there's like one that they always use, and I don't feel like I have enough expertise in the literature to be able to say that the one that they're using is actually the best model. But there have at least been observations that are consistent with a profile that steep towards the center.
Mark?
How about bulge, stellar bulge in the Milky Way? And I thought the prevailing knowledge was that it's really a bar.
Yeah,
So it would not be spherical, it would be elongated.
Okay, I don't have whiteboard to draw on. Yeah, so my understanding is that in projection, what the bar looks like to us is what that boxy bulge or bar looks like to us is like roughly peanut shaped or roughly box shaped, but that if you include a nuclear stellar component, the central component is pretty spherical. Like the outskirts are more elongated along the plane, but the central component is pretty spherical. For the excess, again, this is based on the people who write these papers cite some specific papers on the estimated morphology of the bulge. If the consensus in the field is that the estimate of the morphology from those papers is just wrong, then that would be good to know. But the excess is right. I mean, the significance of the sphericity of the excess is like really dominated by the inner region. In the outskirts, just the excess is falling off pretty steeply. The backgrounds are pretty bright. It's just hard to tell. And so you have quite a lot of freedom. So long as you keep the inner part pretty spherical, you have a couple of degrees. So long as you keep the couple of degrees region pretty spherical, you have quite a bit, like you can make it quite elongated along the plane without making the fit dramatically worse, so long as you only do it in the outskirts. So I think like that's how they're reconciling that. I will say, I mean, like, even if it looked really fully spherical, so then you have the question of how do I get an MSP population like this? And indeed, if you start out with stuff, or with young pulsars for that matter, if you start out with it seated along the disk and then it gets kicked outwards, then this does not give you something that looks like the excess. So there was a paper by Brandt and Coxius from like 2015, which suggested that if you were getting these millisecond pulsars from the disruption of globular clusters, so globular clusters orbiting around the Milky Way had come in too close to the galactic center, got entirely disrupted, spilled out stars into this region, then that would be a way to get a more spherically symmetric millisecond pulsar contribution. Millisecond pulsars live for a really long time, so they could be like the longest lasting relic of these globular cluster disruption events. And so, yeah, so like, I don't think the spherical morphology is, I would not call it a prediction of the millisecond pulsar model, but I would say that it's something that you can accommodate. Similarly, like in the dark matter case, the spectrum is not really a prediction of the dark matter model. Like, until you know the dark matter mass or what it's annihilated to, you don't know what the spectrum should be, but it's something that you can accommodate. Like, you can find models that do it. So.
Yes, Carl.
So yeah, speaking of globular clusters, I mean, we know there's huge numbers of millisecond pulsars in there, largely coming from dynamic formation of binaries.
Mm-hmm.
Is it? I don't know if people have done large Fermi surveys of globular clusters, but for instance, in 47 Tuck, I'm pretty sure at this point through radio observation that we know all the point source millisecond pulsars.
Yeah.
And if you could just get a bunch of Fermi data from that, could you sort of just compare that? And sort of
Right.
test whether or not the point source model is working with that?
Okay, good. So you want to actually, okay. So I think there are maybe like a couple of parts of this question. So you're sort of saying like, can we try our point source detection pipeline on this and see if we can pick up? So I would think that like most of the Fermi's angular resolution, as I said, is not very good. And most of the globular clusters that I think are not very big to Fermi. So like, and most of them will look like point sources themselves. And so then you're not going to be able to resolve more point source-like structure within it. Like the thing that gives us hope in the galactic center is that the excess extends out over a 10-degree region. There's no globular cluster on the sky that's going to be 10 degrees. That said, so you can, well, the spectral argument that I made before is already based on globular cluster observations in gamma rays. Like you look at the globular clusters in gamma rays, you see a bump that looks very similar to the galactic center excess, and then you say, okay, that's the millisecond pulsar spectrum. That's also what we see in the galactic center excess within systematic uncertainties. So the galactic center excess is probably also millisecond pulsars. There's a counter argument to this, which is, you know, as you said, we believe that the millisecond pulsars come from X-ray binaries. So if you think this is what's going on, you can look at the gamma ray flux from globular clusters, look at how many X-ray binaries there are in the globular clusters and say, right, this is the ratio of gamma rays from millisecond pulsars to X-ray binaries. Do you see, so the gamma rays in the galactic center then predict a certain number of X-ray binaries, do you see that population? And the answer is you don't, by like a couple of orders of magnitude. The usual counter-argument to that is, yeah, but globular clusters in the galactic center are really pretty different environments. Like, you know, you don't necessarily need to have the same ratio between the X-ray binaries and the gamma ray emitting pulsars as you do between one and the other. But yeah, so that's, so that's kind of where we stand now. I mean, the gamma ray spectrum of the globular clusters is one of the pieces of evidence for the excess being MSPs. But trying to do more direct comparisons than that doesn't seem to line up, but it may be because they're just such different environments. There was actually a recent paper which looked at a pretty nearby globular cluster, in which where they said, we see gamma rays from this globular cluster, well, possible globular cluster. Their claim is that this globular cluster is actually like the stripped core of a dwarf galaxy. So it has a dark matter component in the center. The claim is that it's close enough that we would have seen the millisecond pulsars in it if they were there, and we don't. But nonetheless, we see gamma ray emission from it. So they want to claim that the gamma ray emission is coming from the stripped dark matter core in the center. And it does have the same spectrum as the galactic center excess. But I mean, this really relies very critically on the statement that if there were millisecond pulsars there, then we would have seen them, because otherwise it's the gamma ray spectrum of millisecond pulsars coming from a globular cluster. That's not super surprising.
Yeah, also the reason we have all the 47 Tuck is because everybody just wants the radio telescope.
Yeah.
47 Tuck.
And it has a huge population of second pulsars that, you know, are consistent with the LMXP.
Yeah, so I'm not sure if the statement that we haven't seen any MSPs in this other globular cluster is really, I mean, they want it to be the statement, you know, therefore there are no MSPs. And I'm not sure if you can actually make that statement, or if it's just, but we haven't looked hard enough. Because, I mean, if you can really say that there are none, then it is kind of intriguing that there is a gamma ray signal from that object. But, yeah.
One last question? Yeah.
If the gamma rays were coming from point sources, would those same sources generate X-rays, and could you see the
Yeah, so, well, especially if they're pulsars, then they should be generating X-rays in principle. Yeah, so the estimates that we've done on this well, primarily not me. The estimates that my collaborators have done on this made it look like radio was probably going to be an easier channel to search in than X-rays. I did a quick estimate for New Star a few years back, and we found that you would need to get very lucky with the X-ray to gamma ray ratio to be able to see the X-rays from this pulsar population showing up in New Star. But yeah, we were talking about Rosita earlier today, and maybe with Rosita you can do better. Because, I mean, with New Star, like, it was kind of borderline. It wasn't, this is completely hopeless. It was just like, oh, well, you need to be sort of right out on the tail of the expected gamma ray to X-ray ratio to see something. So if you have a better instrument, then, yeah, maybe you could see it in X-rays as well.
I think
Which would
that's
be
actually
great.
going to be a key part of the story. eRosita is going to survey the whole galaxy 8 times over its 4-year lifetime, and it's got much better, well, it has hard response, which obviously New Star does, but it's got much longer exposure times with larger effective area. So I think that's going to...
And as we were talking about earlier, I mean, the other thing that eRosita can do is give you a better map of the background. Like, I mean, if eRosita can tell you what the shape of the Fermi bubbles really looks like as you get in close to the galactic plane, then you can build a better model of the Fermi bubbles from that and potentially remove a source of uncertainty in the gamma rays. Like, even if you can't see the pulsars themselves, just having a better understanding of this region might help you figure out what's really going on here. Because, like, at the moment, because we don't really know observationally what the Fermi bubbles look like in gamma rays close to their base, because they just blur into all the other stuff that's going on with the Galactic Center, it's very hard to tell the difference, for example, between the Galactic Center excess having a high energy tail and the Fermi bubbles getting brighter towards the Galactic Center. Like, there is a hard high energy component in gamma rays in the Galactic Center. What it's physically associated with is really hard to distinguish when the instruments that you have looking at have an angular resolution of 0.1 to 1 degree. So.
Okay, if there are no further questions, let's thank Tracy for a great talk.
Very nice, very nice.
Thank you. I mean, it's a bit oscillatory, but yeah, we'll see where we land.
Second place stars, I think, the
I
disruptive
may not have heard of the properly.
Yeah.
ways to produce this.
Okay. Sure. Of course.
Question, so to say.